energy supply for a sustainable RAS, which is short for Recirculating Aquaculture System. My name is Gerard, and I'm going to go through what I've done so far in my project. So, first of all, what I'm working in is built in a bit bigger project, which is called Mass Balance and Energy Optimization in RAS, with special focus on diurnal variations in water quality. And there are in total 3 work packages, as well, when Leila presented herself, she mentioned it. One of the work packages is what she is working on, which is simply put water quality, but it's much more than that. And then I'm basically focused on work package 2, which is the same name as the title of this presentation. So I'll show you a bit of what the RAS or the scope of this project of my work package look like. And here we can see the energy system, which is composed of wind, solar, and wave energy. All of these 3 components, which are there, and they are meant to supply the energy demand of a RAS. And now this is supposed to be an isolated circumstance or an autonomous system. So we cannot depend on being connected to the grid. And that means we need storage either in the form of batteries, hydrogen, or biogas that can be produced from the fish sludge in order to balance the grid when there is not enough harvest. So the end goal of this project would be to optimize this system. So how we can do it to make all of this harvest and storage system as more economical as possible. So we can see here, this is basically the RAS system modeled in Aspen HYSYS, which is a program used for process simulation. It's very widely used in Norway in the oil industry. So this is what the water treatment loop looks like in HYSYS. And it is all based on a real case study. So all the data, all the equipment, everything was taken from that case study, and simulations of the real operation were just replicated. So what's important in a RAS is that most of its water is recirculated. And in this case, it's about 99.7% of the water in the fish tanks that gets recirculated continuously. The other 0.3% would be new fresh water that is introduced to compensate for losses or evaporation. So if we go through the system, we can see that we have some equipment that is used for treating the water. And the key parameters when we are dealing with RAS is the total suspended solids, which is uneaten feed, fecal matter. Then we have the biofilter, where the ammonia gets converted into nitrates. And then the aerator, where CO2 is stripped, oxygen is introduced. And lastly, oxygen cones, where water is pressurized and pure oxygen is injected in the water in order to reduce the volume of water needed to bring all the oxygen back to the fish tanks. So basically, we simulated the whole process, the whole grow out in the RAS, which is 15 weeks. And we wanted to find out what's the energy demand of all the equipment in the RAS, which is the RAS pumps responsible for carrying all the water through the loop, or most of it at least. An oxygenator pump, which is a bit powerful pump, but only draws a small amount of water and pressurizes it in order to saturate it with oxygen. The blower, which will send air to both the biofilter and the aerator. And lastly, the heating demand of the heat pump for the incoming fresh water, which is really small, but still needs to be regulated to keep the temperature of the system. So what I did was simulate all these 15 weeks, and for 2 different scenarios. On the first one, in case A, this was a constant flow of around 24 cubic meters a minute. I was suddenly muted. I don't know why. You all cannot hear me, right?
You're back now.
Yeah.
But I can't see your presentation.
Oh, you cannot?
No.
I don't know why I just got the notice that I was muted. Can you see it now?
Yes.
Okay, that was
Thanks.
a bit weird. So as I was saying, we have the two cases, one with constant water, about 24 cubic meters a minute. And this was replicated from the RAS, like from the case study. And then case B, which was adjusting the flow according to the parameters in the fish tank. So we have all these different parameters that I briefly showed you before: ammonia, CO2, oxygen, and total solids. So we would see which of these is the bottleneck or which goes out of control the fastest. And then we would set some thresholds values in order to decide how much water do we need to keep all of these parameters within these threshold values. And then we would find out how the flow would develop as fish grow. More demand of the system is needed because there's more biomass, they breathe more, they eat more, and then you need to increase the flow. So then you can see in the end how the energy demand of the variable flow case compares to the constant one. In overall terms, there's an 8% less energy demand for the 15 weeks in the case with variable flow, which points towards maybe more or a slightly sustainable alternative for operating a RAS. And even though we see that the peak in the end is higher, the difference is because one parameter which went off the limit in the normal case or in the constant case. So if both cases didn't have any parameter over the threshold, this demand on the constant case would be even higher than it is now, which means the adjusted case would even save more energy. So right now we would have simulated, now we have all the results, the energy demand of the RAS, and we can see at the other side of the system. We want to find out what do we need in an energy system to be able to cover this energy demand. So what I'm going to show you today is the wind turbine and photovoltaic panels models. I'm still working on the wave energy, so I cannot yet show you something definite. But I will be focusing on these two. And the idea is that each of these two types of energies would have a variable power capacity. What that means is that we're not setting a specific wind turbine with specific power rating, but we want to be able to adjust the power capacities of all the systems to see which is the best combination of each one. And then in order to simulate the system, we would have hourly data for both wind speed, solar radiation, and wave ocean conditions for 10 years, which will be the span of time in which the system will be simulated. So let's start with the wind. In here, we have wind speeds for 7 different heights. So the first thing we need to do was to interpolate all of this data into wind speed profiles so that we can, in the end, interpolate what the wind speed is at the corresponding hub height of the downscaled wind turbine, because these are not going to be of equal height anytime. A 2 megawatt wind turbine will be taller than a 1 megawatt wind turbine. So we need to adjust that. So for the wind turbine then, we started with a model, Vestas 90, 2 megawatt, which corresponds to this blue line. And this is the power curve for this wind turbine, just replicated from the specification sheet. So what we did after that was to build the other power curves based on the piecewise equation for the power curves of a wind turbine. And then we adjusted a couple of parameters, which are mostly mainly the hub to tip radius of the plates, and then the power capacity limit of the wind turbine. So this means that both the area swept and the upper limit will be affected depending on the scale of the wind turbine. And as I mentioned before, since a smaller or a less powerful wind turbine is smaller, then we need to adjust the hub height and find out the corresponding wind speed at that hub height. So then we can produce all the other power curves for all the other downscaled wind turbines. And in this case, this would correspond to a 1.6 megawatt turbine. This would be 1.2 megawatt, 0.8, and 0.4. So if we see now solar energy, I said we had two different layouts or two different configurations. One is called S and one is called EW. And that's basically the cardinal direction they are oriented to. So in configuration S, all the panels will be facing south in a single row. And then in configuration EW, they will be facing east and west in double rows, as we can see here in the pictures. Now, the reason we have these two configurations is because even though it's like everyone knows it, or it's a bit obvious that facing a panel towards south is the most optimal orientation, what we want to see is how would these two configurations affect the need for a bigger or smaller battery. And I'm going to explain what I mean. Let's say we have a solar panel in this configuration, or two to make it equal with this example. So two solar panels facing south. You would have a narrower power harvest curve with a peak at noon, and then it drops a bit faster dusk and sunset. So if you have these two panels in configuration EW, you will have a much flatter curve. In overall terms, you might be harvesting less energy in one day, but then since you are not having a higher peak at noon and a more spread power harvesting, what this means is that the mismatch between the power harvest of solar panels and the demand of the RAS might be smaller. So this is the point of seeing these two configurations, to see which one performs better, both in terms of total power harvest, but also in terms of necessary energy demand. Sorry, I misspoke. In terms of necessary energy storage. So to make the models more realistic, we have a little example of how the shading of the panels would be. This is configuration S, and we have both panels, let's say, facing down in the screen. So incoming sun rays would meet the top of the panel in the front row and then cast a shadow on this panel. And what we did in this case was to first calculate what percentage of the panel is shaded. And then we did some other simulations with this specific panel, which has 60 cells divided into 3 strings, so 3 times 20 strings. And we shaded that panel partially to see how the power output of the panel would change. So then we have the relationship between percentage of shading and the power output of that panel. So with this thing and this shading model, we can calculate and predict how much energy you would get out of panels, depending on how much shading you have on them. So this is the explanation for both wind and solar. Now I can jump into an example because we need to see what the energy storage need for a system. And this is the key point of this project. So I'll show you an example first, and then we'll see some sample results. Let's say we have an hybrid with 1 megawatt power of wind and 0.75 megawatt of power of solar in configuration S. This is what the power harvesting would be for 1 year. This is just simulated for 1 year, just to show how it will work. So we have both of the harvesters, and then we have the curve for energy demand of the RAS. As we saw before, this is the curve for a 15-week operation with a break of 1 week in between for maintenance and cleaning. So that's how the continuous operation of the RAS would work in terms of energy demand in a long time. So We simulate this for 1 year, and then we want to see how much energy surplus or deficit we have. And then the key point is we want to see how low we can go on energy demand and still be able to supply energy to the RAS the whole year. So no exceptions in this case. What we find out is here we have the curve of the level of energy stored during this year. We see it has a cap, an upper cap, which corresponds to 78 megawatt hour. That's a lot. But in this example, this is the 90% of the state of charge of a battery. And why is it 90%? Because this is also another constraint of the problem. Since we want batteries to have a prolonged lifetime, we can only allow them to be operating within the 10 to 90% state of charge. So this means that we would need actually a battery or several batteries with a total capacity for 86 megawatt hour in this case. And then on the lower end, a 10% state of charge would have 8.6 megawatt hour. And this is what the bottleneck of the system would be in this case. So if we were to reduce this amount of stored battery, of stored energy in the battery, then it wouldn't be possible to reach at this point with enough energy to cover the RAS. We would either break this condition and supply the RAS with energy at a lower state of charge, or we would keep this and then not be able to supply energy to the RAS. So this is what I mean when I say that we need to find the minimum amount of energy storage required for a specific hybrid, which in this case was 1 megawatt wind and 0.75 megawatt sun, solar. And a little detail, maybe some of you noticed, there's a gap here, and you would think that this line would run parallel. That's actually from the battery degradation model. So as batteries get used and as time goes, they would lose capacity. That was called capacity fade. And yeah, just in case anyone was wondering why this didn't align with this horizontal line. So now we can see some more realistic examples. If we have a set of wind and solar power capacities, which would be a small example of what I will do in the end. So here we have 3 different power capacities for wind and 3 different for solar. And we want to see what's the energy storage demand for these cases. So we run all the combinations and we follow the same procedure we did before. We see for each combination what's the energy storage demand that we have on each case. And we see obviously that the more power capacity we have of solar and wind energy, the lower energy storage demand we would have. Obviously, because you are much more able to harvest energy from both these sources. Now, this was a case without backup or without hydrogen. So the simplest case of all. In the end, it would be much more complicated, and we don't have time today to go into the rabbit hole. But I can show you what would be another dimension in this study, which is having some backup energy in order to cover the moments where there is either no wind or no solar energy being harvested, which are like the bottleneck of the system of this time series. And we can have this comparison. So let's say 1% of the energy demand for the whole year is covered by backup, and this could come from biogas. Maybe you don't remember, but in Work Package 3, there was like a small work package about biogas production from fish sludge. So it could be a kind of recirculating of the energy within the whole system. So if we use this biogas to cover some of the energy demand of the RAS at critical moments, then we can see how much the energy storage demand will fall. And I can go back and forth again so you can see the difference. This would be with this 1% year coverage of the energy demand. And it's mostly here. Like this is a period with very little wind and little solar energy. And that's the bottleneck of the system. So if I go back now, we'll see that what we are doing by having these backup systems is shaving off the bottlenecks of these curves, which allows the whole curves to go down. And in the end, we would want to see, let's say, if we go up to 10 or maybe 20%, that would be maybe too much, but it would be nice to see. How would this affect the energy storage demands of these different hybrids? So, as I said, in the end, we want to run several combinations of wind, solar, and then wave energy once this is done. And then with all of these combinations, we would see what's the energy storage demand required for that hybrid. And then we'll be able to set trade-offs between power capacities of wind, solar, and wave energy, and then the power capacities for the storage of either in batteries or hydrogen. And why is it important? Because in the end, we want to optimize the system. And knowing how these two aspects of the system trade off, harvest and storage, the only thing we would need in the end is just to put a price tag on everything, implement these cost functions for all the components of the system, and then we would know what is best or what is at least least expensive to build. Is it an oversized wind turbine with little storage, or would it be better to have a middle-sized wind turbine with more batteries or hydrogen? So that's going to be the final goal of this project, to find out what's actually the optimal set of energy systems in techno-economical terms. So that is all for today. Thank you for listening.
Thank you very much, Gerard. Let me just stop the recording now.